Hello, I'm Amery and I'll be covering the backend and big data portion of our image colorization project. So after the image processing portion, we now have a bunch of MATLAB data files, which are consisting of the feature vectors, which are the grayscale values of our images, or the L components in the LB color space. Our target vectors are the bin color values from those images, or the AP components. So the next step we have is to move everything to our AW image, where we can do our big data work. The first part of our big data pipeline is to store all of our MATLAB generated files in a easily accessible format. So due to the large amount of data we're working with, we can't use normal methods to store these, such as lists or arrays. So instead, we use e-arrays from the PyTables module. This array type is both compressible and extendable, so we are able to write our data to the disk and append and read them as we need. The e-arrays are stored as hierarchical data format HDF5 files, which is a file format optimized for efficiently storing and managing high volume data. So here's a screenshot of our initialization parameters for the e-arrays. So as you can see, we need to specify the dimensions beforehand. So we input the shape of each feature and target vector, as well as the expected number of data points. The next step is to incorporate our modified VGG16 neural network into the Apache Spark platform. Using the LFIS module, we are able to run distributed deep learning modules at a large scale on Spark. LFIS works by initializing a master Keras model on a master driver and then handles the serialization and segmenting of an input dataset to its workers. So the model is sent to each worker along with a chunk of data to be trained, and then the results are sent back to the master driver, which aggregates the results from all workers to create a final model. So this is a GIF showing this process. So as you can see, the parameters are sent to each data and model worker, and the updates are sent back to the master model to be combined. It's worth noting that LFIS works primarily with the Spark's RDDs, so we can have to convert our HDF5 files in order to proceed. RDDs are an immutable data structure, and they are structured such that it is divided into multiple partitions. These partitions may then be operated on with different nodes of our computing cluster. And while the HDF5 and the e-array file formats were really useful beforehand in managing our large and constantly changing datasets, RDDs were optimal for read-only parallelized compute operations with a focus on the much faster in-memory processing. So that's what we use for the rest of the pipeline. So next, we have our weights and our trained model, and then we can load them into Python with Keras for a colorization step, and then finally into MATLAB to see the output final image. So now I'll cover the platforms and software packages we used and explain a little bit about why we used what we did. So MATLAB was the main platform for image processing. Our project has deep ties with computer vision, so therefore MATLAB's matrix manipulation abilities made it an ideal choice. We use MATLAB for the pre-processing stage, where we read in our images, create the train and test vectors, and for post-processing as well, when we want to view the final output image. Python was ideal for the overall pipeline and algorithm evaluation. It has an API with almost everything we used. It's got a lot of libraries, and its frequent use with distributed deep learning projects made it an ideal choice for us. Between importing MATLAB data files through SciPy and the PySpark API, we were able to integrate all of our software tools seamlessly with Python. Keras and Theano. So for neural network development, we use Keras for its popular deep learning library. It's written for Python and it runs on Theano, which is a popular GPU-friendly mathematical Python library. So they went hand in hand. And then finally, we use Spark for big data manipulation. Spark is a popular cluster computing engine that we've all used, and it's our platform of choice due to its streamlined API and integration with Python. So here is a sample of the results we got from training our model on the Flickr dataset. So from our results, we can see that our classifier, it's working. It's working to choose the most probable color bin for each image. However, it definitely works better for some images than others. So plants, for instance, like the top row, are colored pretty well because green is a pretty prominent feature in our dataset. So like trees, flowers, they all contribute to this. We can see that the leaves are purpley colored, and the model guessed that the white flowers in grayscale were had a hint of green, even though they're actually white. So it's interesting to note that these buds over here were they were colored. You can see specks of yellow and green in this region as well. The second row, you see an image of a beach, and there's a lot of blue and green in the output image. Most of the sky was colored correctly. There's a blue there, and the clouds were also not colored in this region, which is good because white is a gray soil color. And the sand was mostly misclassified, most likely due to the abundance of sky and grass being next to each other. You know, not as much sand and sky. Uh, Feature sets. So finally, we can see an example of a image that was classified and colored pretty poorly. The sand over here, you can see is completely ignored, so there's nothing there. And there's like streaks of blue and green on the edges, which shouldn't be there. But on the plus side, there's some green here, so the trees. So the trees were colorized properly, and the car is black, the sky is white anyways, so they didn't need that much color to begin with. In the future, we may repeat our experiment with a broader or more general data set. As mentioned, the images we work with were straight from Flickr, so these are generally of a higher artistic quality than an average photograph. There were also a very high amount of nature and scenery pictures as well, which may have influenced the amount of blues and greens because of there's a lot of sky, water, and grass. Additionally, we could stay within these artistic boundaries and simply work with a larger data set. There was two options when we downloaded the dataset. There was a massive 1 million grouping, and as well as a 25,000 group dataset, which we ended up using for this project. It'd be interesting to take the million image dataset into account and apply it to test using our current model derived from the smaller dataset and see how accurate it works. In terms of features, if we had more time, we'd definitely like to try this again on different color spaces. RGB, LAB, there's HSV and YUV as well. And maybe if we repeated the experiment with these different feature vectors, you get better or worse results, but it'd be interesting to investigate. Smaller bin sizes as well. So we did use 50 bins for this, which meant we had a broad range of colors for each bin. If you have smaller bins, there's a higher color resolution, which means that it's a higher class problem, as in there's more classes to sort each pixel into. But you could potentially get better results if you train your model well enough. So that's it for our presentation. Thank you for listening.